Okay, this is tutorial number 5 in the present playlist, which deals with contact issues in the 3D Experience uh, FEA solver, which incidentally is the Abacus program. It can be viewed as a continuation of tutorial 4, although I'm going to start from scratch. And the problem that we have here is a shaft, this green piece, which is clamped at the left end and it's made of steel, and a disc here, which is the gray piece, which actually is shrink fitted or press fitted into the shaft, and it's right next to the green piece, so that there's a contact between them. Now, we know how to do this problem as a shrink fit. That is essentially tutorial number 4. However, here, what we also like to do is once this is shrink fitted, then we want to apply a pressure to the face of the green steel shaft and look at the deformation of the whole thing. This has to be done as a two-step problem. And in the first step is going to be the shrink fit, and in the second step is going to be the applied pressure. Okay. Uh, now, let me show you uh, the geometry and the dimensions. It is possible to make this thing as an assembly of two pieces and then create assembly constraints so that they mate, etc. The alternative is to make them uh, in position as I'm going to be doing it instead of using assembly constraints. And notice, by the way, that the diameter, the radius of the shaft is a little bit bigger than the radius of the disc. So what you see here is actually this is the radius of the shaft, which is 20.5 millimeter, and the hole for this disc, which is shrink fitted, is radius of 20 inches, 20 millimeters. That's why this is half a millimeter bigger. That's why the disc has to be heated up and then uh, being slided into that shaft and then let it cool down. That's how the shrink fit process is going to be working. Now, as in tutorial 4, I will create a reference point, which is the center of this hole here, and uh, apply the restraint for the shrink fit stage to this reference point. Okay. Incidentally, I mentioned that rotations can be checked, but rotations are uh, not degrees of freedom of a solid element, and therefore, whether you check these things or not are not going to make any difference. Now, uh, later on, these are going to be meshed with tetrahedral elements, and I'm going to use the contact interference icon. Please watch video 4 if you wonder what this does. And then keep in mind that in the second step, so there's two steps here. The first step is the shrink fit, and in order to do the shrink fit, for example, I fixed that reference point. But then when you apply in the second step, when you apply the pressure, you have to get rid or remove that restraint. So if you go to the next page, here's how you're going to do that. If you look at second step, this is the one that fixes the reference point. Then we're going to remove it, and that's why you don't get any. This does not get propagated there. Incidentally, the pressure is only appearing in step 2, not in step 1, as you can see here. All right, and some information about the general contact interference capabilities in 3D Experience, which is really Abacus. Okay, so let's go ahead and do that. I start with an assembly, and let's create our shaft first. So right click, uh, insert, 3D part. I'm going to assume that these are both made of, these both behave elastically. Uh, the stresses are going to be very high. Obviously, it's going to yield, but we're not going to look at the yielding issue. So this is going to be the shaft. Double click on it. And on that vertical plane, I will sketch my shaft. So first of all, let me draw my axis, an axis here, because this is going to get revolved about that axis. Otherwise, I have to close the curve, etc., which I don't want to do that. Okay, profile. So let me do it like this. We'll clean it up in a minute by putting the proper dimensions there. So that's going to be the shaft. Okay, I don't have to close it because I put this axis, it's going to get revolved about that. Now let's put some dimensions here. So this height is 50 millimeters. Okay, this is 10 millimeter. Okay, and this is going to be 20.5, as I mentioned, half a millimeter bigger than the other one. And let's make this dimension from there to there 80. That dimension was not described in the slide, but anyway, what I've done is this. Okay, now we're going to exit, and we will shaft it to show shaft it. Because there's an axis specified here, it's going to revolve it about that. Good. And this is good. And this is made out of steel, so I might as well go and add the properties of steel to it. So create material, steel, shaft, with pressure. Pressure applied. Okay, so let's go ahead and say okay. And wait for it to appear in our library. The reason I gave it this weird name is that in tutorial 4, I had the same thing but on a different name. Okay, let me refresh this. Okay, so it was right here. So apply on that piece, and then all I have to do is to specify the Young's modulus and Poisson ratio. Please keep in mind that this is a contrived example. These things probably will yield. The stresses are going to be really high, but that's fine. I'm trying to explain the concept. So this is going to be 200,000 megapascal. Poisson ratio 0.3. Say okay. Good. And now I'm going to insert the disk. So all the way to the top, right click, insert, 3D part. It's right there. Double click. On that same vertical plane, I will sketch, because I'm going to draw things in position. So I do it so that this is going to be touching that face, basically. So I'm going to do a rectangle here and put dimensions. So dimensions, let's see, this thing is going to be based on the drawing. I believe this is 60 and 10. Yeah, this is 60 millimeter, and this is 10 millimeter. Okay, and these are going to be touching. So this and that, coincident, right click coincident. Okay, good. And then the dimension from here to the axis is going to be 20, half a millimeter smaller than the one for the shaft. This is going to be 20. This is going to be slightly, you can see that, slightly below that of the shaft. Okay, good. Well, because we want this thing to be revolved about that line, I'll draw an axis here so that automatically it gets revolved. Doesn't matter where you draw it, as long as you draw it there, it's going to get revolved about that guy. So exit, and then shaft it, and that's good. Now, what I'm going to do is to create a reference point right at the center of the circle. So let me hide that for a second. While I am in the disk, so I'm going to go to Essential, point, and there's going to be center of a circle, and that circle. So this is going to be my reference point. Okay, and of course my disk is in shaft is in hiding, so I can bring it back right there. Okay. Now the only thing that's left is the material for that. So tools, create a material, and aluminum disc with the pressure. This is the example basically. Okay, so let's see for a second. I think it's this, isn't it? I'm pretty sure it's, let's refresh this. Oh, I'll make it bigger. Right, aluminum disc with pressure, right click, apply. Let's get rid of this, apply to that. And the only difference is the Young's modulus here is going to be 70,000 MPa. So structural, abacus multiphysics, mechanical, elasticity, elastic, 70,000 MPa. 71.3, Poisson ratio 0.3. All right, good. So let's go all the way to the top, save everything. Okay. Now we're going to go to the meshing stage, which is structural model creation. By the way, you can also, without going there, you can also do it like this: right-click, insert a representation, and for the representation, you can select the finite element representation. But I'm not going to do it like this. Okay, so I'm going to switch workbenches or applications, structural model creation. Empty FEM, wait for this next window to show up. It says there are two parts here. Which ones do you want to participate? If you miss this window, then you have to do that manually yourself. Okay, I'm going to say, okay, both of them. I want both of these to be present. But in the event that you miss this by any chance, let me cancel that. Let me cancel that. Say no. Say you miss this. Say, okay, so how do you do this? You go to setup, there we are, contributing shapes, and then you select both of them. Because it's easy to miss that unless if you close that window quickly, it's going to disappear on you. All right, so there we are. Let's do the meshing, very simple tetrahedral meshing. So mesh, let me unpin these so that I can see my mesh stuff. Here, tetrahedral. Let's do the disk first. Incidentally, if they're missing, they're in hiding, so let's bring them in the front. Oops. Oh, sorry. Okay, let's do this. Maybe it's missing from here. Yeah, a shaft is missing. And over here, this one is also missing. Okay. All right, so we're doing the shaft first. There's a shaft. These are the sizes, same thing that I had in the slides. Right there, these are the slides. Okay, so mesh. Okay, good. And do the properties for it. Properties, solid. This is the shaft, right? A steel. Good. And let's do the meshing for the disk. Same numbers. These are linear, by the way, linear elements, terrible elements, but that's okay. I'm just explaining the concept here. Steel and this part body is going to be aluminum, right? Okay, so the solid model has been created and meshed. Save this. Now we're going to go to, oh, before I do that, something that I forgot when I was doing the tutorial 4, then I have to come back to it. I want to create that coupling. So first of all, let's get rid of this, or let's hide these meshes. You can do it from here. Okay. Uh, Under the connections, there is this coupling. Okay. You click on that. It says, what is the first support? Let me hide this shaft. The support is going to be this circle, and the other support is going to be this reference point, the point that I created. Remember I created this point? Okay. And it's going to be kinematic, and all of these are checked. Although I said that it doesn't matter whether you check these last 3 or not, but I did check it. Okay. So I did create my coupling here. Okay. Good. Now, let me bring the thing that's hiding to the front. It's probably in front. Yeah, good. So now we're going to go to structural scenario creation. Step 1 is when we do the shrink fit. Step 1 is when we do the shrink. So structural, this is actually the mesh that we're going to be using. We haven't got to the step 1 yet. Okay, this is, notice that this is the case 1. There is a red exclamation mark here. That means we have to specify a procedure, and you do procedure static step. That is going to shrink fit step. You click on it. Okay. So let's make this thing total. This is dummy time, duration 1 second, dummy time. Initial times increment is 0.1. That's what I do, and we say okay. All right. Let me hide all the stuff here. So let's go ahead and get the visibility manager. Don't show me the finite element mesh. Good. Okay. Now, this end is capped. Okay, so let's go ahead and go to boundary conditions. Boundary conditions. Let me unpin this, unpin that so that I can see what I'm doing. Okay, the boundary condition. Fixed displacements. Again, rotations don't matter here, so I just check these. Okay, and that point, because we're doing the shrink fit, this point we're going to keep it stay in the same place. Please take a look at the tutorial 4. So we go fixed displacement on this coupling. Now the coupling, you can select it from here, or let me get it from there. The coupling was done in right there. We can do it from here, right there. Okay. The difference is that I mean a vertex. This is I mean coupling, and I'm gonna say you cannot move in the translation direction y, and you cannot rotate about that y axis. This I don't believe it has any value, but I checked it. If you don't fix this thing when you do the shrink fit, this will fly away. Okay. Now, we need a interaction. Let's create the contact property, which is friction coefficient. Specify 0.1. Okay. We do a surface-based contact. So if things don't work out, we're going to flip these. But for now, I'm going to select for the main. For the main surface, I'm going to select the shaft. For the secondary, I'm going to select the hole in that disk. Okay, and don't forget to change the contact property 1, because the top one is the default, which is frictionless. This one we specify friction coefficient of 0.1. I forgot to do this thing in tutorial 4, then I had to come back and fix it. We say okay, and this is going to be what is needed for our contact interference. But there's one more thing. That face is pushing against the face of the shaft, so I need another one. This face, sorry, cancel that. Another surface base. This face, generally speaking, you take the one that's stiffer. So let me not take that one. Let me take the surface of the. Let me get. Okay, so this one is going to be that face, the less stiff face, which is the aluminum. And for the main, I'm going to select the surface of that shaft. So let's see. So these are hiding, so you have to get them here. Shaft is over there. Bring it into show mode. Okay, let me hide this. Okay, so for the main, I'm going to select this. Let me try that. Yeah, good. And then we say okay. And this one also, contact property 1. Okay. So we have two. Notice that we have two interactions here. Where is that? The first one is just the properties for coefficient friction specified. This one was for the shrink fit, and this one was for the side faces. Okay. Now we're going to do contact interference, and the contact interference is for the first surface-based contact that we created, right there, surface to surface. So this one is going to be the shrink fit. You say okay. All right. Now I can run this, and assuming that nothing was forgotten, we get the shrink fit stage. Okay, so let's go ahead and do that. Then we have to come back and do some adjustment to the certain boundary conditions and apply the pressure there. So let's go ahead and pretend that, well, let's go ahead and do this thing before we apply the pressure. Okay. All right, so this is going to be just one step. Later on, we're going to add another step. So if things don't work out, by the way, I'm going to come back and flip the direction of these uh, interaction branches. Okay, so let's go ahead and simulate. First, do a model check. Okay, a scenario check. Any obvious trivial mistakes may pop up in the stage before we actually run it. I'm pretty sure this one is going to be fine. Good. I'll close it, and now we're going to run it. This is the running stage, but the running of only the shrink fit stage, as if this thing was done a shrink fit before even you clamped that end. Okay. All right. Here's the iteration, which is the counterpart of monitoring the Abacus CAE program. Assuming that there are no convergence issues, it's going to go fast very quickly. It's going to go through very quickly. And I remember in tutorial 4, I did this thing with interference and without contact interference, and they gave me the same answer. So here we just went and did the interference, contact interference anyways. I don't anticipate any issues here, so we should see some stresses developed in the shrink-fitted pieces. So we close that, and this is step 1. This is the last stage. You can see that there is stresses developed here. Okay, good. Now we're going to do the following. We're going to go back to scenario. So procedure, another static step. This is going to be step 2, and I'm going to make again the time step, total time step 1, and initial time increment of 0.1. Okay, because yeah. So and then say okay. So notice that here we have our seconds. There's a step 1. There's a step 1 here, which was shrink fit. I could have called this thing shrink fit. And there's step 2, which is going to be pushing. Now, for pressure, we're going to apply the load here. So we go to load, pressure on that face, 1 MPa. Okay. The only thing is that we should not hold that disk fixed at that location. Remember, that reference point was essentially clamped, because when I said don't translate in Y and don't rotate, although rotation doesn't play a role, translate in Y basically stays there. But because we are applying a pressure, that should be actually easy to move. So here's how you're going to do this. If you go to right click, feature manager, this pops up. It shows you step 1, all the stuff that we need in step 1, and all the stuff that we're doing in step 2. Notice that step 2, first of all, there's a pressure of 1 MPa, and it's not in step 1. We know that. It should be. However, this was the one that enabled us to fix that disks. No translation in Y, no rotation in Y. So I can put the cursor there. See that the cursor is on this line here. Right click, remove fixed displacement 2 in step 2. So we say okay, that's gone. So what I'm showing you here are these slides now. This is the original one. This is when we got rid of it. And of course, now, assuming we haven't forgotten anything, this is done. You can either do the stuff from here. Okay, this is step 2. I don't want to run step 1 again. I'm going to run step 2. So that being the case, it's better to do it from there. See that? This is step 2. And just check it. I don't anticipate anything unusual, because this is essentially, I haven't done anything there. And this is the scenario checked. And finally, the run of step 2. I'm not going to run step 1 again. Now, these could have been done at the same time, shrink fit and the pushing stage could have been done at the same time, one after another one, and then a full run of both. But we decided not to go that route. Okay, and then here is the run of step 2. And then say, okay, let it run. I mean, this is a simple problem. It doesn't matter whether you run step 1 or not, but generally speaking, step 1 took a long time. You don't want to spend more CPUs again to replicate that one more time. Let's do monitoring here, iteration. One thing I don't like, oh yeah, step 1, it was taken the last you know what? I think that it's doing it from the beginning. It did it from the beginning by the look of it, which I don't particularly like, but anyway. ran, looks like it ran step 1 also. Okay, done. So close this. Okay, and we can close that. Okay, let's go. This is step 1. So this is the stuff that we had already done, and I thought it was not going to do it, but it looked like it ran. Okay, so for example, initially, of course, nothing, and then the pressure fit or the shrink fit is done, and it reaches, for example, that stress. Okay, and then you go to step 2 when you start pushing. Step 2, the first step is coming from the shrink fit only, and then you begin to push. These better change. And they change, but not by much, okay? So let's look at the displacement, okay? Step 2, it changes, but it doesn't change by much. So you can see that these displacements are changing, okay? But for stress, I cannot see any significant changes. Let's look at stress one more time, okay? What we can do is let's go and change the pressure to 10 times higher, and let's see if it makes a significant difference. So we go to static step 2. There's the pressure. Okay, let's make this thing 10. Okay, and run it one more time. So simulate. So this was a two-step process. First one is shrink fit, and then once the shrink fit is done, then we apply the pressure on that face. And we didn't see any significant changes in stress, but made the pressure 10 times bigger. Let's see if it makes a difference. I mean, in principle, obviously it should. Okay, so this is step 2. Yeah, this is 5,720. You can see that it does change. Okay, it should.